Everyone, and welcome back. So this time we're going to be going through a procedure for how to solve these problems using all these new equations we've gone into. Now we're not going to stop there. We actually are going to do an example together as well. So let's jump right into it. So first off, what we're going to do, we're going to select a convenient, that's the key word here, convenient inertial coordinate system. Rectangular, normal tangential, cylindrical coordinates, they can all be used. But make sure it's from a convenient location. You want to simplify things, especially angles. Second, draw that free body diagram showing all external forces, none of the internal ones, that are applied to the particles. And you want to break them into components. Remember triangles. Forces are just triangles. Then draw a kinetic diagram. I honestly hate this. If you don't want to do it, don't do it. It just helps you figure out what direction acceleration is going to go. Finally, you're going to, or not quite finally, but you're going to apply the equations of motion in their scalar component form, and you're going to solve those equations for your unknowns. And then finally, if you have to, you're going to pull in your kinematic relations. This is going to happen a lot as we go further along. We're going to have our equations of motions, they won't be enough, and so we'll have to come back to our kinematics. You never get to forget this. Just because we're outside of chapter 12 doesn't mean that we forget our kinematic equations. So let's try out an example now. Okay, what do we have here? Well, we have a box, okay. Box has 100 Newton force pulling it to the right. It's a 25 kilogram block. And the spring has a stiffness of 200 newtons per meter. And originally it's unstretched. What does it want us to do? Well, it wants us to draw the free body diagram and kinetic diagrams of the block when S is equal to 0.4 meters. You're like, wait a minute, what? Yes, we're not even having to solve this problem. We're not even trying to figure out how fast it goes back here. We're just going to draw the free body diagram when this is 0.4. Okay, so what's our plan going to be? Well, you're going to define an inertial coordinate system. Where is it going to be? You're going to draw the block's free body diagram, which is going to show all external forces. I won't tell you what they are though right now. And then you're going to do the kinetic diagram. Now, I guess this is like kind of like a pre-example example. However, I'm still going to do the same thing we always do. So you're going to have a few seconds right now, well, a few minutes for you, a few seconds for me, to try out this problem. So, 3, 2, 1, and you're back. So hopefully that was enough time for you to finish this problem. You did it quick, you worked hard. Or maybe you paused and took a while. Either way, doesn't matter too much. It's just two pictures. So let's see how it goes. Okay, so first off, we can have an inertial XY frame, and we can fix it to the ground. So now we're going to draw a free body diagram of the block. So this inertial reference frame right there is fixed to the ground. It's not going to move, it's not going to change. Up, Y is up away from the ground, and to the right is our positive direction. Then we have a whole lot of stuff here. Well, 1, we have 100 Newton force going to the right. 2, we have our normal force pressing up from the ground. We have our weight pressing down on us. G is the value of gravity, it would be 9.81. And then we have to figure out, well, what is our force from our spring and what direction is it going? So that's not always necessarily very easy, but I didn't ask you to break anything into components yet. Okay? I didn't say break it into components yet, and so in this particular case, you just have to figure out the slope of this line to be able to fully finish our problem. So let's jump back here again. Okay, if this is 0.4, this is 0.3, well, we have everything we need. So we know this is 4, that one right there is 3, and we're good. These multiplied by 10 to make them whole numbers rather than leaving them as fractions. The values are the same. Now, if we're trying to figure out exactly what this equation is, we can, if we want to, leave it as is. Stiffness constant times the delta, how much it changed. But we might want to say, like, okay, well, how far did it actually get stretched? Well, initially it was 0.3 meters. And since this is the hypotenuse, well, we used a squared plus b squared equals c squared to calculate the hypotenuse. So 3 squared plus 4 squared is equal to 5 squared. It's one of those nice little triangles. And so since it's 0.4 and 0.3, this would be 0.5. It's all coming from Pythagorean theorem. Okay, now that we've done this, we have to figure out our kinematic diagram. So how do we, sorry, not kinematic, kinetic diagram. Well, it's quite simply, the block will be moved to the right. Now, the acceleration can be directed to the right if the block is speeding up, or to the left if it is slowing down. Now, where does that come from? How do I get 25? Well, what do you think? How do I get 25? That's going to be the unbalanced forces. Measure the unbalanced forces, because this is going to cancel out. It can't move up or down. That's not going to happen. But the left and right, that is going to change. And so at this particular point, I have 40 newtons pointing at this angle. And so if I think to myself, okay, well, let's look at this and see if I can figure this out. So I have 4/5 of that pointing in this direction. Okay, so 4/5 of that. I think I'm starting to see this now. Yes. So 40 times 4/5 is going to be what? It's going to be 40 times 8, which is going to be equal to 32. And so we'll have a force of 100 minus 32 pulling it to the right. And so that tells us that it should be going to the right. It should not be going to the left for this particular problem. I didn't have to go that far. It's all fine. But you can. You can go ahead and see which direction it should be pointing based on the forces. And sometimes based on common sense. Now, the 25A right here, that is simply the mass right there, and the acceleration, which we did not calculate, though we almost calculated it, I just didn't go quite that far. Okay, so that'll be it for this time. Thank you all for listening, and I'll see you all later. Have a wonderful day. Bye-bye.